Recording is rolling. It's Tuesday, March 17th. Yesterday, you got to Turntable Friction Lab. Somebody turned in today, but if you didn't, you can turn in today, or if you don't can't turn in. I do want to debrief that with you guys, show you guys what an ideal model would look like. We'll do a circular motion review. Now, this will pace out however it paces out. You guys have your notebooks out or some paper off the notes. There's some paper on these desks. You need that. Okay, and then universal gravitation probably pace up. We'll see how this paces out. We go too fast with this, and we can always pull up an FRQ if we need to. But I want to get this circular motion and gravitation quiz to you guys Thursday, and then Friday can be a make a vacation, but it's a Thursday, or we'll see how it picks up. Right. All right. So you guys go with what we're doing. We're doing. All right. So, right. Here's get a picture of what you guys did yesterday. Right, you guys had this turntable. You guys would take one of these masses and pop them. Right. And if you spin it slowly, it sticks on the surface because there's static friction. So you spin a little faster. You spin a little faster. At some point, it's going to break friction. And it's going to slide off. And at that point, if you can maintain that angular velocity right there, that omega, and somehow determine what that is, maybe with the stopwatch you guys have, right? We'll go through it, right? Then you can determine what's the coefficient of friction, right? So there's a little proof over here. So this is what I would do, right? Create a three-body diagram. So you got the weight down, the normal force up, which should just kind of balance each other out. Okay, so could you guys say this normal force is effectively equivalent to this mg weight? Yeah, and that'll be helpful for the substitution later on. Okay. And then, guys, what this friction force here always points which direction? Yeah, always towards the center of the circle, as long as this is spinning, as long as it's rotating. Because this friction force is acting as the wet force. Centripetal force, and that's the first line I have right here. Is the friction force acting as the centripetal force. Once you have that, everything else is just series of substitutions, a little algebra to get to the answer. Okay. So friction force, isn't that coefficient of friction times normal force? Right, so that's why I subbed right there. Right. Now, guys, if we're talking about static friction, that's why I went with the inequality, because you can spin it a little faster, a little faster, a little faster until it's breaking point. But if it is a breaking point, can you just go ahead and make this an equals? Is that okay? Yeah, guys, this should just become equal. If you just did equals on your paper yesterday, that's perfectly fine because it would have been a breaking point. Okay. All right, how about centripetal force? What now in terms of linear speed, can that be mv squared divided by r? But what about in terms of this angular speed omega? What's the expression for that? Yeah, m omega squared times r. Yeah. All right, so this is all going to show up in the review later today. Right, I think I have a poster with O'Neill cylinder on it. You guys see later today. Thank you. I can see that. All right, so we got this. Oh, and then guys, what's the next substitution? What do you think?
mg.
Yeah, this normal force is this mg right here. Right, okay, so that's right there. Right. What do you guys see now?
The mass cancels out.
Mass does cancel out. Yeah, so if you treated mass as an independent variable and maybe you made some kind of graph, it would have been maybe a boring flat line because mass ends up not mattering at all. Right? Now the gravity field is locked in place. We're locked in surface of Earth. The coefficient of friction is like some number. That's what we're trying to find. Okay. And now, if you did want an independent variable, you could have moved this to different locations on the surface, could you? And change this radial distance from the center. You guys could do that. Yeah, maybe I should put the R over here, just like it's getting too cluttered with much stuff. Okay. And then, guys, if you had this right near the center, or pretty close to the center, do you have to spin it really fast or really slow for it to break friction and slide off? Yeah, incredibly fast. Yeah, like a centrifuge. Okay? There was a group I saw yesterday that put it like right at the center, and they were spinning it. It's like it's not sliding off. It's not sliding off. Yeah, because it was like right at the center. Right? But if you put it right near the edge, then you don't have to spin it nearly as fast. It'll just pop right off. Right? Okay, so there's some kind of relationship between these two. Right? Anyway, you do an algebra rearrangement. You guys are right. The math ends up putting everything up. Although the material matters, so you want to be careful you didn't like change from this to this because the materials would be different. Right? Right, it ends up being this expression here. Okay, so let's read the music of this equation while we're at it. Okay. So this is saying that if you were able to move it further out and it still wasn't breaking friction, that would indicate, so if R is increasing and it's not breaking friction, that would indicate what kind of coefficient of friction, more or less. Yeah, greater and greater, right? Because if there's hardly any friction at all, it'll slide off real fast. If there's a lot of friction, it's like really sticky on there, then you could put it way out and it would still stay on, right? some idea for this angular speed, right? If you have to spin it like really, really fast, like a centrifuge, like, it's so hard to get to break, and this is really, really fast, wouldn't that also indicate a very high coefficient of friction? Okay. And what if you wanted to create a graph out of this? Guys, can you create a graph that would linearize? Here, I'll give you guys a head start. Give you guys about 1 minute here. How could you take this equation, somehow rearrange it, put some variables on some axes? There's more than one way to do this, right? So you can create a linear graph. You guys know AP loves linear graphs. And maybe the slope of that graph could eventually lead you to being able to solve for a view. Can you guys do that? Okay, go ahead and do that. Some of you guys may have said that on your write-up yesterday. I don't know if I know when I read these later because some of you had to turn on today. Got that? Right. How can you take this equation, rearrange it? Okay. Your variables, remember, could be R and omega because mu is a constant, G is a constant. But you can change the R as your independent variable, and omega could be sort of the dependent variable. But how could you create a linearized graph where maybe the slope could tell you something about coefficient of friction? All right. Here, I'll show you guys what I would have done. Again, there's one way to do it. So copy down this equation. Mu as I'm going to change this to an equal sign. So okay, equals gets be at the breaking point. Okay, and then let's go omega squared R on G. So we got some expression to define them. But here's maybe what I could do. I could put omega squared on one axis and R on the other. No, it wouldn't be R. I think it would be 1 over R. Let me rearrange this. So I could go omega squared equals coefficient of friction times gravity field of Earth. Okay. And then wouldn't I have to actually divide by R? So it'd be 1 over R. Isn't that true? Is that true? Like that? Okay. Now, if I do that, I could say, here's my y-axis. Here's my x-axis. Okay. And then what would this represent?
Slope.
Yeah, this would be the slope. And it would be a linear line. Right? So, linear curve. So I'll put omega squared here. This would be in radians per second. That whole quantity being squared. Okay. I got 1 over R here. That could be in 1 over meters. Right. And then if I plot all the points, yeah, they should line up in a straight line. They're pretty close. Right. And I could say, yeah, let's take the slope of that line. That's slope. Okay. And whatever the slope is, rise over run, that slope. Okay. That would be equal to coefficient of friction, coefficient of static friction multiplied by the gravity field. Right. So then if I wanted to find the actual coefficient of static friction, I wouldn't have to further divide by the gravity field, wouldn't I? Okay. Alternately, you could take that gravity field and embed it in the x-axis. So you could go G over R here, and then the slope would be exactly coefficient of friction. Right? Or you could divide it over and divide it over here. Right? So there's a few different ways you could do that. You can linearize that data. Right, guys, that. Right. 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 I have a write up. Okay. So here's the question you should come up with. What's the coefficient of static friction between the lab weight and the surface of the turntable? Or something like that. Just pretty close. Right. That's what you're trying to find. You can do this with a ruler and a stopwatch. Those are the tools you guys had. If you put something like a triple V balance, that's okay too. But oftentimes AP will provide you some given values for the masses, so they don't expect you to measure that necessarily. Okay. So set up, place a lab weight of known mass on a horizontal surface of a turntable. And we're of course eventually going to spin this thing. That's why it's a turntable. Use the ruler to measure the radial distance of the lab weight from the axis of rotation. Speed up the rotation of the turntable until the lab weight breaks friction and slides off. Maintain that angular velocity at that moment. Use the stopwatch to measure the time for 5 revolutions. Now, at this point, here, I came in about 20 minutes through class yesterday, and I gave you guys a hint. I said, well, this is the table I would have set up. Now, theta in revolutions. When you eventually get to your calculations, do you want theta to be in revolutions? No, it's easy to measure because you can just say, oh, it's passing the same point over and over. But you really want radians, right? Guys, how do you go from revolutions to radians again? Yeah, just times 2 pi. So if you measured 5 revolutions, could you do times 2 pi? You get the number of radians. And then however much time it took on the stopwatch, could you just divide those two? You get how many radians per second? What's the angular velocity? Okay, so 1 step at a time. Marching towards that. Okay. Multiple trials, repeat 3 times and record the average value to reduce experimental error. You guys know that's always a point on AP's write-up. Okay. Determine omega, the angular velocity. So it's 2 pi times 5, 5 being number of revolutions. You didn't have to do 5 revolutions. Some guys did 10, that's okay. Right. But that's how many radians, then divide by the time for that turn, right? That gives how many radians per second. That's okay. And that was this pretty much that poster we were just looking at. Where'd it go? Somewhere I had it. I don't know. Where did I just put my? Lost there. Okay. Right, but it was this right here. Right, so we're setting centripetal force as the friction force. The friction force acting as centripetal force. Okay. The whole derivation I just showed you guys. Here's how to find coefficient of friction, and so you can come up with a conclusion. Now this right up, I'm just doing it as if you. There's no independent or dependent variable. You just put it on, and you can just find a single answer. Okay. But even better if you can come up with like a whole table of values like this, right? Whole table of values and then linearize all the data. Okay, so that's a skill AP wants you to have too. Okay, here. Okay. All right, so you guys go with that.
Yeah.
With an ideal answer to your lab from yesterday. All right, so let's flip over to PowerPoint. All right, and again, you guys have your notebooks out. And so here's at the tail end of forces, and we're saying, hey, what would happen if something was going around a curve? Okay. And this is really a setup for circular type motion, isn't it? Anyway, okay? Because now this friction force between the tires of the road is forcing the car to the left, allowing it to make a left-hand turn. Remember, these are the forces on the car. I'm not looking at the forces on the road. I'm just looking at the forces on the car from the road. Similar idea with the pendulum swinging, right? Hey, why is it that if it's hanging at rest, the tension is equal to the weight, but if it's swinging back and forth, the tension is more than the weight? Oh, because now there's a net force, which is centripetal force, right? That's all leading into circular motion. And so let's go over variables and units. Guys, what is theta? Or no, sorry, I just gave it away. Or angular theta is angular displacement, and that would be radians, right? What does omega measure? Angular velocity. Right? Sometimes you'll see rotational velocity, and that could be in what? Radians per second. What is alpha?
Angular acceleration.
Angular acceleration. Rotational acceleration. Right? So if it's speeding up spinning. Radians per second squared. What is
acceleration?
Centripetal acceleration. What's the unit?
Meters per second squared.
Meters per second squared. Yeah. FC. Centripetal force. Could be newtons. Okay. Now, the bottom half of this table is really rotational mechanics. So, because these bottom 4 lines are not going to show up on the quiz this week, but of course, eventually. Okay. That was all unit, later unit, 5, 6. All right. Analogous variable. So time is still time in seconds. Okay. Instead of saying how far meters, now how far is the turntable turned in radians? All right. We got velocity. We got acceleration. Okay. Okay, and then yeah, the bottom 4 rows are really more like future units, but here. Well, but by the time we did get to inertia, that's what mass was in a linear sense. What was inertia in a rotational sense? There was I, which is sum of m r squared. Do you guys remember that? Right. Okay. Something like that. All right. And then we had Newton's second law and momentum and energy. Okay. Ooh, guys, what goes in this blank right here?
Theta R.
Yeah, theta times R. Right?
Yeah.
So how far is this turned times how far are you from the center? They'll tell you how far you moved in a linear sense, like in meters. Yeah. Now, guys, the catch here is theta. Can theta be in degrees? No, it has to be in radians. You guys are looking at 1 radian right there, about 57 degrees, pretty close. All right. What goes right here?
Omega.
Yeah, omega R. Omega R. About right here.
Alpha R.
Alpha R. Okay, so if you have the angular value, you multiply by your distance from the center, that gives you the tangential value, right? Okay. Rotational kinematic formulas. What's yeah, I get the order they're coming up here. Okay. All right. Can you guys know these are just analogous to the linear kinematic formulas? It's like distance equals speed times time, or velocity times time plus 1/2 acceleration times time squared. All right. You know what? Let's see. All right. You guys are just looking at them. See if you guys can write the 3 kinematic formulas for a turntable. Write the three kinematic formulas for turntable. They're the same as the linear equations, except just replace every linear value with its rotational equivalent. Right, time is still time. That one's still the same. Right, can you come up with the three kinematic formulas? It's got paper. Got also files for you. Everybody's got paper back here. Got paper. Got paper. On what? Oh. All right, what do you guys come up with? I'll check the work in front of you. Is that what you wrote? Did you guys write those three formulas? No. You guys know here. Flip my screen here a moment. Right. Of course, these formulas are right here. Right? AP writes them a little differently, a little different order. Right? They do it in terms of position rather than displacement and so on. Right? Right, so you do have this, but I think it's a good idea to also have those imprinted on your brain anyway. Okay. Let's do turntable slows to a stop. Because what do those three graphs look like? We got displacement, velocity, and acceleration. Of course, the angular version of all those. For a turntable, let's say a turntable slows uniformly to a stop. Slows uniformly to a stop. Slows uniformly to a stop. Take one more. Reference room here. So you guys are coming up with for slowing to a stop.
No.
All right. Oswald got careful.
Well.
Because as it's slowing to a stop, is it moving backwards or forwards?
Wait.
Is it still moving forward, right? Close. Slip got all right. Jessica got Lily got okay, yeah. You guys get these.
Where's your Alpha go?
All right. Okay, so let's start with this middle one. Guys, if it's slow to a stop, it started at the beginning of the interval with some angular velocity. And if it goes to a stop, what's its final angular velocity? 0. And if it slows uniformly, then this should be a straight line, right? Straight line. Right? Guys, if that's a straight line, what does the slope of that straight line represent? Angular acceleration, which say that's a constant negative value. So on the angular acceleration versus time graph, how do you graph a constant negative value? Boink. It's like that. That. Right. Same thing. Right? Now the tricky one is angular displacement. And so some of you guys got this. Right? So what do you guys draw for this one? Yeah, upside. Well, it's not a root. It's an upside down parabola. Upside down parabola. Right, with the vertex right at the top. Okay. So notice that as it's spinning, it's accumulating angular displacement. Right, still going forward. It's just slower and slower. So it's gonna be concave down. Call it that. Right. Right, you guys got that? Slow to a stop. Right. Hey, does this look like a car braking to a stop? Look like, yeah, if you just X, B, and A, yeah, same shape graphs. Oh, okay. There's how fast it was spinning at the beginning. Okay. Oh, okay, and then there's all these other connections too. Got all that. All right. Got some trivia here. Go through this trivia. Got different technologies. Foucault pendulum. I played that video for you guys, didn't I? Where the Earth was spinning, and then it looked like the pendulum was rotating, but really the pendulum was going back and forth, and the Earth was rotating underneath it. Right? Some universities around Florida have those focal pendulums. If you go to one, look, right, you do a little scavenger hunt for those. Coriolis bet. You guys ever notice all the hurricanes rotate counterclockwise? Right, it has to do with crossing latitudes and low pressures. Right. So if you fire this cannonball from the North Pole, the Earth is spinning underneath it. It's going to look like it curves off to the right. Although, really, the cannonball is going straight. The Earth's curving. The Earth's turning. All right. So triple force. All right, so you guys had this lab. Okay, now guys, there's an equation for the force. Guys, could the weight down here? You guys see this weight right here?
Yeah.
Since that's just hanging out, and this is in true static equilibrium. This bottom weight is. Is this bottom weight equal to this tension? And this tension is equal to this tension. Okay. Let's say this circle is approximately horizontal. Okay. So, is make as many of those graphs as you can. As many of those graphs. Okay. Now, if you know the equation, guys, if you remember the equation that this all leads to, then you can know what all the graphs look like. Go ahead and whip off a bunch of axes. Grab as many of those as you can. Yeah, well, AP could ask you any of these, right? Yeah, gotta make sure you know all of them. Gotta know them all. Yeah. How does every variable relate to every other variable? I guess how does the linear speed, how does the tangential speed relate to everything else?
I understand it. They all like jobs, but like wow. I figured it out. I don't know about them.
Okay. All right, so I got the PowerPoint. I see the order these are going to come up. Okay, the first one is V versus R. Okay, so did you guys write this formula? Because guys, if you wrote that right there, you could know what every single one of those graphs looks like. Right? And relating V or V squared somehow to all these other three variables. The centrifugal force, which is this tension, but it's equal to this weight anyway. Right? This mass, which is guys, what is this M? Is this M the hanging mass or the swinging mass? The swinging mass. Right? So it's one being held in a circle. Right? And this R is this radius of curvature here. Right? So how about V versus R? What if you made that graph? Guys, could you cross multiply the R? Can you do that? Cross multiply the R? Right? And then if you graph V squared versus R, that should linearize. But if you do V versus R, don't you have to take a square root? Yeah. So I think that would make a square root relationship, wouldn't it? Right? And that's, of course, holding all else constant. Right. Where's the PowerPoint? There we go. Okay, so V versus R would be a square root. Right. Which means V squared versus R makes a what shape? Linear. There you go, linear. All right, next one. How about V versus F? Right, F being force, tension, the hanging weight. Right. Well, let's see. Hey, look at this. Guys, if I cross multiply this R and I do F times R, you guys see that? Right. Couldn't you, whether it's F times R or R times F, aren't they sort of occupying the same space? Yes. Right. So is it going to create the same shape? I think it's the same basic relationship. I think it should be. Same basic relationship. Right. So what shape would you draw right here? Right, square root. Right. So as you make this hanging weight heavier, you do have to spin faster, but it turns out to be a square root relationship. Which means that V squared versus the hanging weight is going to look like what? Yeah, that's another linear. All right. Next one's going to pop up as this one on the top right. Right. So the speed is a function of the swinging mass. Ooh. Well, guys, as you make this mass heavier, what happens to the speed you have to spin it? Or go the other way, right? What if you started off with a pretty hefty weight or pretty hefty mass up here, and you made it lighter, lighter, lighter? Then how would you have to spin it?
Slow.
What?
Faster.
Yeah, then you have to spin it faster.
I'll
Right.
get there.
So, do you think there's an inverse relationship between this mass and how fast you have to spin it?
Yeah.
I think so. Yeah, like if you had an empty string, you have to like a centrifuge, huh? Right? I think some kind of like that. And with the equate, this is of course all leading to an equation. You guys made the graphs first when you guys did the lab, and then we fit into this equation. So we're looking at the relationship between these two right here, this mass and this speed. Because whenever you see two variables multiplied on the same side of the equation, they have an inverse relationship, right? Or you could divide the m over. You could do v squared is proportional to 1 over m. Right? Okay, is that it? Right, so okay, so I see something to do with inverse. So I'm gonna take the reciprocal of one of those. Let's say the m. So v versus 1 over m. Okay. Now maybe this linearizes, maybe not, or at least it should be closer to linearizing, right? Okay, it didn't quite linearize, but it does look like a square root, like these others are square roots. Ah, and I know how to go from a square root to linear because we just did it twice. I have to square the v, or that's one way to do it. And right. At that point, when that linearizes, okay, now we know the full proportion, and that'll lead us to the equation.
Absolute proportion. Which is wow.
Right, okay. Alright, so that all led to ooh. So what's that formula right there? mv squared over r. And what if you're just looking at the centripetal acceleration? What would that be? V squared over r. Okay. Now that one is the only one that's on the equations here. Put the screen and point this out. Okay, it's right here. You see centripetal acceleration is v squared over r. Okay. Yeah, so that's the only one. Give it. Okay. Now, if you write centripetal forces mv squared over r and use that to derive something, I don't imagine they would count off for that. Okay, so they should get credit for that. They don't give you centripetal acceleration in terms of omega, in terms of angular velocity. But what you could do is you could combine these two. This a is v squared over r, centripetal acceleration, and you guys see v is r times omega right there. Could you do a little substitution there? Okay. You could, and then you could get the. I think I have an O'Neill cylinder heat up pretty soon. Okay. Oh yeah, there it is, O'Neill cylinder. Okay. So guys, once you make that substitution, what's this formula and what's that formula? Go ahead and write those two real fast. See if you guys remember those. What is the centripetal force and centripetal acceleration in terms of not a linear speed, but in terms of how fast the whole turntable is rotating? Ooh. Hey, what did you guys come up with? Did you do m omega squared times r and omega squared times r? Okay. There's no fractions anymore. It's just multiply. Multiply. Okay, so here, let's walk through the story, see why it makes sense. No, we're out in deep space. You guys see we're out in deep space? The Earth is way off in the background. Right? So there's not significant gravity around. Right? Which means that if this was not rotating, wouldn't those guys just be floating around like astronauts? Just floating around. But if you give this thing a little spin, if it's big enough, it might feel like gravity, really hard to distinguish that there's not actual gravity. Right? Like, how about this guy right here? He has some mass. And there's now, see, he wants to fly out this way tangent to his motion, but the floor underneath him is holding him in with this normal force. And that's his apparent weight, isn't it? It's holding him in. And that could be this force right here. It's acting as a centripetal force. And all these different guys here, you guys think all these different guys could be different masses and have different weights and or apparent weights and so on? Right? But do they all experience basically the same artificial gravity field? Yeah, they do, because that's this one on the bottom right. So they all feel like they're in the same artificial gravity field. Except maybe this guy in the ladder, if he climbs the ladder up too much. Because, guys, if this guy climbs all the way to the central axis right here, this dashed axis, what gravity field does he feel right at the center? Yeah, 0, because you could be multiplying by 0 on each of these. Right, now he's back to being just floating around again. He pushes off, just float off into space. Right, you guys got that? Alright, check out. Ooh, turntable with springs. And so I've seen a FRQ in the past that looks kind of like this. Right? So I'm gonna attach this mass to the spring. Let's say that the frictionless surface. Don't worry about friction. That doesn't exist right now. Maybe put little wheels on it or something, right? And give this thing a spin. Got some omega velocity going on. Super, right? Isn't that gonna stretch the spring? You guys see the spring stretching? Oh, by some amount x, right? Some amount x. Let's say the mass positions at some distance r from the center, and that's a constant r from the center. And round it goes. Here's a free body diagram of the one on the other side. If you guys have an idea. Right. What do you think could go in that green box? Something's gonna go in that green box. What do you think? Probably goes in that green box. Oh, is there some kind of centripetal force going on here? Centripetal, right? Provided by what actual force? What force providing the centripetal force? Spring force. Yeah, there's no friction. Not on this one. Right. But the spring. So the spring is holding that mass in a circle. Is that true?
Yeah.
Hey. And what's the formula for spring force? Careful.
Okay.
Kx.
Oh,
Kx. Right. And then I got m omega squared r. Yeah, right. There's spring force, there's spring energy, different things. Right. Okay. Right, you guys can come up with that. Right. And then, okay, I see 5 variables floating around: the k, the x, the m, omega, and r. Okay. So, if you know any 4 of those, you could solve for a 5th. If you know a number of those, maybe you could make some kind of graph out of that, maybe kind of like we did earlier. Okay. There's a few different ways you can go with that. All right. We're back to your lab yesterday, but I debriefed with you guys at the beginning of class today. See if you guys remember the whole process. Go for it. Right, the whole process. We just covered it about half hour ago. Can you guys rewrite that whole process from start to end?
You're gonna go on. You can start with that. And you start about. Yeah, I'm just gonna start with the square. Wait.
There's a free body diagram part of it, which that you guys can get. There's that algebraic derivation, which you guys should also be able to get. We're all finding that.
Again, wait, I need more.
If there's some hints at you guys. So if that's spinning and that point is staying on that surface, why? What force is making it stay on the surface?
Friction.
Friction? Right, the friction force is acting as the what force? Right. Now, do you know some substitutions for each one of those forces?
Yeah.
I could substitute this, I could substitute that. Do you remember what variable ended up canceling out by the end of the process? Ooh, the mass you guys were saying? Right. Right, you guys ready? You guys ready?
Yeah.
All right, here we go. All right, this is how I would. There might be like 2 or 3 different ways to go about this, right? But here's what I would do. I would do free body diagram. Got the weight down, the normal force up, which is same magnitude. Cancel out. Right? And then the friction force is acting as the centripetal force, pointing towards the center as it's rotating. Right? The friction force is acting as the centripetal force. I know friction force is coefficient friction times normal force, and centripetal force. Well, in terms of angular speed, it's m omega squared times r. Right? Now, if you were, again, looking at just the breaking point where the coin was just about to slip it, you break friction slide off, you could just call this equals. You could just go equals all the way down. Okay? Next substitution, I know that normal force is equal to the weight mg. And next step, I know that the masses cancel. And if I want to solve for coefficient of friction, I can just divide down the gravity field. Okay? So you should get that right there. Here's the full process. Show of hands, how many of you guys got the whole thing? Got the whole thing. Ooh, pretty good. Yeah. Looks like most of the class. Pretty good.
Yeah. Wow.
All right, you guys got all that. You got all that. All right. All right. All right. Here's the table. I guess you're yesterday. Guess yeah. There's a blank column. Sometimes it's nice to have a blank column, or AP will give you a blank column so that you can manipulate something. Like for example, maybe I should have done even more than one blank column. Because guys, if you square the omega and maybe the r, you do 1/r. Right, that could be helpful because you can create this graph of omega squared versus 1/r, which would linearize, right? Which is something I could totally see AP asking. Okay, something like that. All right, like that. Ooh. Oh, these two terms right here. Which term do I use and which term do I never mention? Yeah, so centripetal is a center-seeking force as perceived from inertial frame of reference, non-accelerating, right? Like an outsider's point of view. Right? AP always has you guys solve puzzles from an inertial frame of reference. Right? This other term, centrifugal, like centrifuge, is like if you're on the rotating platform, which would no longer be inertial frame of reference because you would be like, moving in a circle. To you, it feels like you're being thrown out, although there is no actual outward acting force. It is, you would perceive it that way if you're on the rotating platform, though, right? So sometimes called fictitious. It's not really there. Okay. Okay, so again, in this class, we're going to solve everything in terms of inertial frame of reference, centripetal. Guys, if you're keeping track, we've got 3 different kinds of acceleration at this point in the class. 3 different kinds. What's one of them? What's the first one you guys learned? Yeah, just linear acceleration. Okay. I might call it tangential if it's on a turntable because it'd be like as going in a straight line. It's like the same thing. Right? Tangential level, right? Can you guys think? What's the unit for that? What's the unit? Yeah, meters per second squared. Right. And can you guys think of some formulas that might relate it to other types of acceleration? Got something going on in the space right here. Aha, aha. Right. So when you guys first learn this, it could be a car speeding up or slowing down in a straight line. Can that be a change in velocity over change time in a linear sense? Okay. Now, on a turntable, this is one of the first slides we did earlier today. Could be alpha times r. Right. Speaking of alpha, that's the next one I got. Guys, what is this alpha right here? Yeah, rotational acceleration or angular acceleration. No. For both of these, for this green one and for this red one, does the turntable have to be either speeding up spinning or slowing down spinning? Yeah. It has to be one of those, right? It can't be. It can't be constant angular velocity because if it's constant angular velocity, isn't each one of these equal to 0? Okay. Right. Okay. And then okay. Here's that. Here's that. That's okay so far, right? Right. But what's this last one? This yellow one over here. What's this? Centripetal acceleration. Centripetal. And what's some formulas that go with that? You could do v squared over r. Let's go ahead and get omega squared over r. Right. This is centripetal force divided by the mass. That'll get you there too. Right. Now, guys, this one on the left, could you have a constant angular velocity and this one still exists? Yeah, that's the only one that you can have with a constant angular velocity. Right? And that one's pointing towards the center, isn't it? Yeah. Yeah. Ooh. What's the minimum speed to get that ball around the top of it? Let's say it's on a string. Is that okay? It's on a string. Right, got a ball on a string. Right. Or maybe I think I had a cup of water, didn't I? Did I have a cup of water in class? I did this a long time ago. Yeah. Right. And it was spinning around a circle, the water staying in the cup. And I went a little slower. It's like, uh-oh. Hey, I wonder if there's some minimum speed so that the water doesn't fall out of the cup. That's what you guys are solving right now in your paper, right? Okay. You guys are doing this whole process. I can see you asking this. What's the minimum speed to go around a vertical loop? Around the top of a vertical loop. Okay. Because realistically, is that ball right there changing speed as it goes up and down the loop? Okay. Where's it going the fastest?
Bottom.
Yeah, the bottom. It's going fastest at the bottom. Right. Where's it going slowest? At the top. Right. And that's the one you gotta be careful of, because that's where the water would be most vulnerable to fall out of the cup. Great, let me grab this phone call. Alright, we're back recording. Alright, so did you guys come up with let's do free body diagrams, then we'll do this derivation. Guys, what's the free body diagram on? Let's start with the one on the bottom. What does that look like? It has
Gravity.
it has a weight going up. It has a weight and maybe a tension force because I said the ball was on a string, right? I just didn't draw the string because it's got too cluttered. Okay? But it's got a weight down and a tension force up. All right, now when you get to the top, which is really what we're focused on, what are the forces? Yeah, guys, is it the same weight down as it is here? Is it the same weight? Yeah, Earth's still pulling on it the same. Okay. And how does the string pull? Down? Yeah, the string's got to pull down, doesn't it? Okay. Now, is the string tension going to be more or less magnitude than it was at the bottom? It's got to be a lot smaller, right? In fact, it could approach zero. If it gets to zero, you just barely gets around, doesn't it? Ah, right. Okay, in which case the weight would be acting as the only force with centripetal, wouldn't it? Okay. Yeah, I think the string tension is maximum at the bottom and minimum at the top. Okay. Right, yeah, the string tension is changing all the way around. Okay. All right, what do you guys write for net force at the top? And I guess you're looking at it right there, aren't you? It's what plus what? Yeah. The weight of the object wants to pull it down, and the string tension is also pulling it down right at the top. Okay. Okay. Now, you guys see where this is going. I skipped a bunch of steps, and at the very end it says V minimum at the top. Guys, if it's V minimum at the top, what simplification do you think you can make to this equation right here? Which of these three terms goes to zero? Yeah, the tension at the top. If I check that cup of water, go a little slower, a little slower, a little slower, I think this tension's getting smaller, smaller, smaller until it just goes to zero, right? So, how about this? Before I show you the next line, guys, what do you guys substitute for net force at the top? Something, something over something. mv squared over r. Yeah, that sounds right. mv squared over r. There you go. mv top squared over right, equals mg plus the top, or tension at the top, and the tension at the top. We'll strike that. Oh, what variable cancels? Yeah, the mass. Yeah. And then if you want to solve for this v, can you guys finish off the algebra and solve for that v? Okay, go ahead, solve for the v at the top. Okay, what's the minimum speed to get around the top? Okay, maybe someday you guys are designing roller coasters for a theme park, and roller coasters got to make it around a vertical loop. Got to know how fast it's got to go minimum. Okay. All right, what do you guys come up with? What's the v minimum at the top? Anybody get it? Yeah, walk around, see if you got this. Just a little algebra right there.
I gotta write it down.
All right, yeah, see, Lily got it. Yeah, Cody got it. Okay, yeah, Lily got. Okay, yeah, you guys getting this? Get this. Yeah. Get the answer. All right, root GR. Is that what you guys got? Root GR. Right. If it goes any slower than that, then now it's gonna be slack on the string and it doesn't make a circle shape. Yeah, yeah. Right. Oh, let's look at Ferris wheel and ball on string. Now we were just looking at ball on string, right? But now I've got 8 locations, and how about a Ferris wheel going around 8 locations? Right? Now I put the weight on all these. Guys, the weight's the same all the way around, isn't it? Earth basically pulls the same, right? But there's some other forces at play. So, okay, I guess we're starting with the Ferris wheel, right? Could this be you sitting on a scale? Yeah, I think this was a recent quiz question, wasn't it? You're sitting on a bathroom scale as the Ferris wheel goes round and round, and your weight fluctuates up and down a little bit, right? So, guys, as you go up, what do you think is happening to this normal force, say, at the very top as you're sitting on scale? Do you weigh a lot or weigh very little up here? Right. How about this? There's another poster coming up that has a car going over a hill. There's a car going over a hill. If you go too fast over a hill on a car, could you fly off the hill? And do you feel weightless at that point? Weightless? So if you go too fast over the top, do you feel closer to being weightless? I think this normal force is getting small. Right? And what about if you go through a valley? Do you feel really heavy going through a valley? So let's follow this around. Ah, look, now the normal force is getting big. And there's a full circle. Okay. Okay. Now, a ball on a string, guys, the string can only pull one way. Which way does the string pull? In the direction of the string. So this looks a little different. If the tension changes, then it also gets bigger at the bottom. But the string only pulls along the direction of the string. Okay. A little different. There's 16 questions AP could ask you right there. Do you guys ever notice? Okay, here. let's see free body diagrams. All right, so there's the weight of the cart, and then there's the normal force from the belly pushing up. Right? Oh, guys, do those balance out? Is that in equilibrium? No, no. Which force is bigger? Normal force up. I think you feel like you weigh more than you normally do. Why? Because this cart's on a what kind of surface? Curve surface? Is it? It's being as it's moving forward to the right. It's also being pushed up by the track, isn't it? Right. And so what about at the very top? At the very top, what does it look like?
Both down.
Both down. Yeah. The weight's still down. That's the same as before, right? Yeah, and the normal force on the track also pushes down. Guys, notice these are the forces on the cart. We're not looking at the force on the track. We're looking at the forces on the cart. Okay? Like that. All right. Yeah. You guys ever notice that roller coaster loops usually have this teardrop shape? Ever since the 1970s, they do this. Right? They don't actually go to circles. Do you guys remember why? Right? Because guys, look at this radius of curvature. It starts out pretty big, and then it gets kind of medium, and it gets kind of small. So it's a gradual change of radius. If it was just going to a circle, that centripetal feeling would hit you all at once, like bam. Right? So it's more gradual. Right? There's my car in a hill, valley. Okay, so you guys remember that? Kind of did that already. Right. All right. Well, had a few more, but we're about to be out of time here, so we'll pick up there tomorrow, and then gravitation's coming up pretty soon. All right, and then look for a quiz on Thursday.